A very good day to Dr. Muhammad Zainul Abidin bin Abdul Aziz. First of all, I would like to introduce myself. My name is Malini and my groupmate Ranggita and one Irne Aida. In this video, we'll be explaining and discussing about our assignment, which is stepped impedance 6th order maximally flat low pass filter using microstrip line for WLAN application at 3.6 GHz. I will start off by explaining the low pass filter design process. The low pass filter design process involves a number of steps, which first the frequency of applications needs to be identified. In this work, we chose to design low pass filter circuit for wireless LAN application at 3.6 GHz. We also know that the cutoff frequency for the design should be higher than the application frequency. Therefore, we decided that the cutoff frequency to be 5 GHz and the operating frequency to be 8 GHz respectively. The Butterworth filter, which is also known as maximally low flat filter, was used to design the circuit. The insertion loss, or also known as attenuation for the Butterworth filter, was chosen to be 20 dB. Using all the parameters that was chosen to design the low pass filter, the normalized frequency was calculated using the formula of omega naught over omega c minus 1. Using the formula mentioned previously, we managed to obtain 0.6 for our normalized frequency. Therefore, we used that value and also the 20 dB insertion loss to determine the number of order. The number of order was determined based on the maximally flat filter prototypes as shown on the video. Therefore, the intersection between the insertion loss and the normalized frequency that we obtained was 5. Therefore, we chose one number higher, which is n equals to 6. Next, we need to refer to the table for the Butterworth low-pass filter design as shown in order to obtain the constant values of G. We chose N6 because the number of order that we got was 6, therefore we took the value of G1 to G7. Based on the constant value that was obtained, we designed a low-pass filter circuit with respective value of G and also resistor value, which is 50 ohms. The final step to design the filter circuit is to convert the G values into respective capacitance value and also inductance value. The formula shown in the green box was used to convert the G value into respective capacitance and inductance value in order to simulate the circuit using the CST software. With that, this is the low-pass filter circuit that we obtained after converting the G values into respective inductance and capacitance value.
So this is for the circuit simulation. CST software is used. However, the frequency for the low-pass filter should start at lower frequency and stop at higher frequency. The higher frequency should cover the operating frequency that is equal to 8 GHz. By that, then we can check the response of insertion loss as we have decided earlier. Therefore, the low-pass filter is simulated in the frequency range of 1 to 10 GHz. The following plot shows the S parameter as a function of frequency. So this is for the S parameter plot. And then next, this is for the plot of S1 and 1, and this is for the S2 and 1, and this is for S1 and 2. So lastly, this is for S2 and 2 plot graph.
Based on the scattering parameter graph that we obtained from the simulation, we first need to analyze the scattering parameter of S21. We checked if our cutoff frequency, which is 5 GHz, falls on the negative 3 dB line. The frequency value is around 5.63 GHz at minus 3 dB, which means that the filter is working in an optimum condition. The difference in the cutoff frequency at minus 3 dB is acceptable due to the possibility of shifting during the simulation. Next, we analyze the scattering parameter of S11, which is also known as the return loss graph. From this graph, we can observe that the range of frequency from 1 to 5 GHz, which is the cutoff frequency, lies below negative 10 dB. This proves that the filter circuit is working in a good condition because the range of frequency from 0 to the cutoff is below negative 10 dB. For the S12 graph, we can observe that it is similar as the S21 graph. And finally, for the scattering parameter S22 shows a similar graph as S11.
So before we designed the 3D simulation, we did the Kuroda's transformation to get the circuit and the values. Kuroda's identities are used to convert an open parallel stub segment of transmission line to an electrically equivalent shorted series stub section of transmission line. As a result, an identical S-parameter matrix with the same functionality is generated. The technique is advantageous when developing distributed element circuits with two distinct configurations. Filters are an excellent example as open parallel stubs are difficult to implement in the physical layout, whereas shorted series stubs are simple. Kuroda's identities are just a listing of two port networks that are equivalent. By equivalent, we imply that their scattering, impedance, admittance, and transmission matrices are identical. In other words, we may substitute a two-port network for its counterpart in a circuit without changing the circuit's behavior or characteristics. Thus, we chose n equals to 6 in the Butterworth table for this design, as there are 3 capacitors and 3 inductors with a resistance of 50 ohms. We solve it one by one using Kuroda's second identity and then multiply the values by 50 ohms. We may proceed with the 3D simulation procedure by determining the width and length using this value.
The substrate that we chose for the microstrip 3D design is the FR4, and the height of the substrate is 1.6 mm. The relative permittivity for the substrate is 4.4. Based on these values, we calculated the width and length for the microstrip to be designed using the CST simulation software. All of the formulas shown below was used to find the length and width of the microstrip line.
So we designed a ground structure Butterworth step impedance low-pass filter. For the low-pass filter, copper anneal material with dielectric constant 4.3, substrate height and loss tangent was employed. The capacitor of the proposed microstrip Butterworth low-pass filter design has a rectangular shape slot. Result shows that the step impedance low-pass filter has a cutoff frequency of 5 GHz. This point has a very acute cutoff with low insertion, return and insertion losses in terms of S22 and S12. Overall, the return loss matching response improved to approximately -35 dB. The filter should be able to transmit signal with minimal insertion loss in pass band and strong attenuation in stop band. We got the best insertion loss at -35 dB without altering the filter order. So this is for graph S11. The line is placed at -3 dB at 5 GHz. And for the graph of S21, the range of frequency 5 GHz is also at the range of -3 dB. Next, for the graph of S12, it is same with S21. And next, for the graph S22 is also same with the graph S11. So as we can see, it has been proposed and realized on copper dielectric at 5 GHz Butterworth low-pass filter employing open circuit stops, which has been tested. By altering the length of the stop, the open circuit stop filter also allow for simple adjustment of the stop band performance of the filter. The design of microstrip low-pass LC filters using slot ground structure have been investigated. The measure shows the signal almost completely and use copper as the dielectric, resulting in a circuit that is ideal and passes the majority of the signal at the desired frequency, while the graphical structure is maximally flat and produces the least amount of insertion loss.